Here you see this is our source here. So here we generate the photons, we illuminate our sample, that's this over there, sample, so that you have an idea. It's around 5 millimeters. And then the electrons are coming out and going to this port that you see over here. So this is our analyzer. So this is the scheme out of that. So illuminate the sample with light, electrons are coming out and going in. So you see these dimensions here around, so quite far away. So that's why in our conventional XPS, we can measure, let's say, with these conditions. If we want to study a catalyst, in a catalyst, we have to go to much higher pressure. Remember, I've said that in this Haber-Bosch process, we are working at 300 bars. So let's say we first start a lot of orders of magnitude lower, so going to the millibar range, we see that we have already a lot of problems to use this technique. If we have a chamber in the millibar, electrons would not reach the analyzer level. So in the detector, we have to have at least 10 to the minus 7 millibar. So in order to be able to use the technique, so what we have to do is two things. We have to reduce this aperture, that's quite long, quite large here. You see this is 5 centimeters here around, and we have to get it much closer. So first point, reduce the aperture, make it only 20 microns wide, so the gases that are here, 1 millibar, cannot enter too much in our analyzer. And the second point is to get the sample as close as possible, so that the gases are reacting here, but they cannot enter too much. So getting the sample at a 550 micrometer range. We illuminate from the side, and this is what we call a near-ambient pressure setup, what we have here, for example, in our university, or what we will also study in the synchrotron radiation facility. So this is like, it looks like, again, the chamber. We have now, instead of what we had before, so this very open configuration, now we have a very closed configuration. So at the end of our analyzer, we have this, what we call the nozzle, tiny opening here. We are getting very, very close to the sample. So actually, this here is our, let's say, end part of the analyzer. Light comes from the left. And you see this is the reflection in our sample of this cone. And you see the opening, you see it here just on top of my mouse. This is the opening where the electrons then go in. If we want to get to even higher pressure, so here we go to the millibar range. If we want to go to even higher pressure, then we can also do. So now we can do experiments, for example, in Hamburg, that we reach 1 bar, and then it's even more sophisticated. So instead of this simple cone that we have a double cone, and the gases are actually flowing inside. So the gases are coming here to our surface. We illuminate from the side. And in this case, what we are creating is what we call a virtual cell. So here we can have a pressure up to 1 bar, so an atmosphere. And the drawback of all is that these machines are very sophisticated. So it's very complicated. So if you have a look, for example, from this side to this opening, you see this is where the gases are entering. And then this inner part here that is going to the analyzer, it's not open. So there are very tiny holes in the range of several micrometers. So in order that not all these gases that we have here around, so here we have 1 bar, here we have 10 millibar, that all these gases go inside of our analyzer and would actually absorb all our electrons. And such experiments are now possible. There's one of such an instrument in Hamburg, and there will be one here in Spain, in the Alba synchrotron, in the near future. And you see, of course, it also depends on the flow. So as much gas as we flow through there, see, this is the, let's say this is the different flows, as higher we will get the pressure. So for example, if we want to go to 1 bar atmospheric pressure and the flow of, let's say, 4 liter per minute, something reliable for a catalyst, then we would have to bring the sample to 40 microns from the from this cone. So we will still start first with the photoemission simple one, the NAPs that we can do, for example, in our lab, and this was done here in Max 4 in the synchrotron. So we have our sample, this curved sample that we have seen before. So here we have some steps, here it's flat, here we have some steps again, and we have this cone looking to this part of the sample. We illuminate from the side, so from here, and let's say this is again a video that will not work. So basically what we do, we basically move up our crystal and we taking, let's say, the spectrum corresponding to that, and then you see for each part of the crystal, we will have a different, let's say, spectrum that we can address. And out of these different spectra, then we can make for each point, so we measure here, we measure there, next, 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 next. We can make some image plot where we have actually the intensity of this light, and this what we can analyze over here. So different angles, here a lot of steps, no steps, here we again a lot of steps, and you see we have a different response. Now remember, I have shown you before that with this laser experiment, we were seeing that in one part of the sample, in this B step size, we get it quite strongly activated, here not so much. And this is what we can do with our curved crystal approach. So basically we have different surfaces, and this is, let's say, the power of this X-ray photo emission spectroscopy, what we can address. So we have the core level, for example, this is the carbon 1s. So carbon 1s comes from this CO that actually is at our surface. And we see we have two peaks. So again, the power of XPS tells us that one peak corresponds to the carbon monoxide atom of a, in this case, of a platinum or rhodium atom. And the other part, the green one, corresponds to a carbon monoxide in some of these hollow positions. So you see we have more, let's say, bondings here around. They change a little bit the electron cloud around our CO, and that's why it changed the inner, the energy of the inner electron of the carbon. That's why it's just moving a little bit left-right. Now we can address this. This is on the 111. We can go to the side parts, so to this 221, to this 331, so on the side parts of our sample. We can make the same spectra, and then you see it has changed already. And this change, first of all, the carbon is going down. And then you see also we get some new parts over here. So this pink and this light blue emissions. And let's say now this is the, let's say, some carbon monoxide atoms on the step part, for example, here on the top and here on this bridge part. And now we can study that. We can go step by step. So this was, let's say, the poison stage where it is not active. Now we can go where we get actually our catalyst active and see what happens. So if you start from the A-type step, you see nothing happens, everything looks the same. But if we go further down, so if we go to this part in the center, then you see already the atoms that are in the hollow positions. The CO molecules gets reduced. The other one is not affected. And if we go to the B-side step, then it's not only that this gets reduced, the green one, but also one component. So this bridge atom completely disappears. Now the bridge atom was just, that was sitting on our corner, on our step in between atoms. So, and when we have now a look to the oxygen, so then we see the oxygen out of the CO and also of the oxygen is now able to dissociate. So we're making space. So one of the, let's say, top, one of the hollow positions of CO goes away. We have space. We can dissociate oxygen, and oxygen now is on our sample. And here we can now make the CO oxidation process. So this oxygen will taken away by some CO and so on. And you see this is even more effective on these B-side steps. So I will go a little bit faster. So this was what we had before. So basically the resume is that on the B side steps, we empty our steps. We do not have any more CO sticking. We have place. We can now dissociate the oxygen. And here on this oxygen, we can combine them with the CO to make the CO2. On the other side, this does not take place because our step edge is different. You see when you have a look, so this step edge is actually a square, while here this step edge is a triangle. So this triangle, because in this part we go towards a 1, 1, 0, and in this part towards a 0, 0, 1 direction. Now we can do the same with platinum. This is also a video that will not work. And basically here on the video, you will see everything illuminates at the same time. So platinum is different to rhodium. And this is a little bit point what we can study, why this happens on platinum in a different way than what I have shown you before in the rhodium. This part, I think I will not have much time, so I will go very quickly. The second reaction, it's the NO reduction. So this would be the ideal reaction that we want to do out of our car exhaust. So this NO is coming out, also CO is coming out. Both gases we do not like. So what we want to do, we want to combine them to CO2 and nitrogen. This would be the best reaction we can do. So we will also need some catalyzer, other two reactions that we had already. And the catalyzers we will do here are basically, again, rhodium and iridium. And this experiment now, this is done in Hamburg. We will go to more or less atmospheric pressure, so 1 bar. Again, this is like it should usually work. So we have these 2 stages of the catalyzer, some poison stage, some active stage, and in between the, let's say, the ignition, the onset of the reaction. Again here, so we have our catalyst, rhodium, in this case, completely poisoned. We have the CO and NO sitting on top. There's no space that we can split one of these NO to N and O, and nothing happens. And we go to the active stage. Basically, you see here, this is the part where we actually split our NO. So then we have a nitrogen and the oxygen. Oxygen goes towards the left. We produce the CO2, and the nitrogen can combine with another nitrogen to produce our, let's say, molecular nitrogen. Or what you see also here, we combine them with another NO. And this is the reaction what we do not really like, because we would produce N2O, what is also a poisonous gas. So here we can actually study selective things. I will go quickly over. So basically, we will do here just one comparison, rhodium 111, rhodium 112, because curved crystals does not work in this setup. Very quickly. So basically, at the poison stage, you see here now our temperature. You're not anymore at room temperature. It's already poisoned at 300 degrees centigrade. So we would heat in our catalyzer, this catalyzer to around 400-500 degrees centigrade in order to be able to do this reaction. So here we are, again, we have the nitrogen oxide sitting just on top of our sample. Everything is poisoned. And the advantage of this ambient pressure here now is that we are not doing only photoemission on our sample, we are also doing photoemission on the gases that are in between the analyzer and the, let's say, the sample. And then we have a direct look of our, let's say, gases that we produce. Poison stage, of course, we have only the NO that we could move in. When we watch the nitrogen, of course, when we watch the carbon, then of course we would also see the carbon. Here we just have watching to the nitrogen. And in the active stage, actually, we remove this adsorbed nitrogen. We have only, let's say, the split nitrogen, so the atomic nitrogen here. And now this atomic nitrogen can react with another atomic nitrogen, produce the N2 molecule, or this N2O. And this is what you see here. So the gases that we are creating here. Basically, we have our NO that reduces a lot. We are producing nitrogen, the molecular nitrogen gas. This is what we want. But you see, we are also producing a tiny bit of this N2O. So if we now can compare, you see in this part with this rhodium 111 crystal, we get a 15% of this N2O, what's actually a sink that we want to avoid. So there were some previous studies some years ago that were done in the millibar range. So here we now at the, again, we have to move a little bit away. So here we are at the bar range. So, and these guys found out that in the millibar range, you produce a 5% of the N2O. And now here, as we get closer to the ambient conditions, we produce much more N2O that we want to avoid. If we do the same now on the 221 surface, then you see already on this 221, we have from the beginning in this poised stage, we are already able to split part of the NO at the steps. So we have a tiny amount of the atomic nitrogen, but it's not enough that we can do some products. So you see there's still everything with NO that we produce. But now if we go to the active stage, then actually we see we get again the atomic nitrogen. So the NO just disappears, and now we can analyze again our gases that we have. And here you see the NO is reduced a lot. We get a lot of the molecular nitrogen, and the N2O is much lower. So you see here the turnover has changed. So if we compare them, this is one of the last slides I will show you. If we compare them, you see if we do the process on a 111 phase, then we have a turnover of around 60%. And out of the 60%, we have 15% of the N2O. In the case of the 112 surface, our turnover is 70%, a little bit higher. That's already good. But you see, we can reduce the N2O quite a lot. So it's having only a 5%. So this is, let's say, the design of our catalyst. So we now know that using such a crystal, such a phase is much better than using such a phase if we want to have a large turnover of the atomic nitrogen and a small of our N2O. So this, let's say, surface is much more or better selective to the process we actually want to have. This I will skip. And so come to some conclusions for you. So I hope I was able to show you that this curved crystal approach that we are doing here, so not having just a flat surface, having different surfaces, let's allow you to study on the same crystal, on the same sample, physical and chemical properties, and they react in a different way to, let's say, the amount of defects, the amount of steps that we have in our surface. So we are doing this near ambient pressure photoemission and ambient pressure photoemission experiments here, and they are well suited to study such catalysts. And with our curved crystal approach, they're even better suited to carry out some important reactions. And again, so this important environmental and artificial reaction can be studied in very detail. I've shown you there mainly on the CO oxidation and a little bit on this NO reduction. And in the future, so what I've shown you today are very simple reactions. In the future, we will do a little bit more complicated reactions. So what, let's say, in order to be able to reduce relevant greenhouse gases such as CO2 or CH4 and convert them, or let's say store them or convert them into usable fuels and reduce the amount of these, let's say, greenhouse gases in our atmosphere. For example, here you see on the bottom one of these catalyzers that we want to address in the future. So this is, for example, some oxide material, cerium oxide, zinc oxide, on some curved copper crystal, and we want to do, for example, suction reactions with CO2 with hydrogen, and we want to go out there ethanol and water, so in the ethanol using as a fuel. With this, I will finish. I want to acknowledge the people who were involved in this work, so from our university and from the synchrotron in Hamburg, where part of the experiment was carried out. The part of the ambient pressure and the part of the near-ambient pressure was done in the Lund University and the synchrotron of Sweden, and also people involved there. And that's it. I hope I was able to show you a little bit some things, and I'm open to answer to some questions.
Thank you very much for the nice talk. Thank you very much for the nice talk. And now we have the question. It's a session for the question. You can ask your question online, or you can unmute yourself. We have one question from Yasir. Yes, Yasir, you can go on.
Okay, firstly, I would thank Professor Frederik for his insightful lecture. My name is Yasir Yassin. I am a chemical engineer with a bachelor degree. I have a bachelor degree in applied chemistry and chemical technology and a master degree in industrial computational mathematics. So I combine the theoretical tools with the experimental tools. I want to ask Dr. Frederik about the ability of making a heterogeneous catalyst computationally. Do you do this in your labs? Do you have a DFT programs or certain software or programming language in order to do quantum modeling? Because my recent research right now is in battery storage. I am in the department head of new energies and storage system, also in National Energy Research Center, Sudan. So this lecture was very insightful for me. Thank you so much again. My question is, because of the current war in Sudan, we cannot do the experiments in labs or something. That's why we hold experiments by doing it in the computer or laptops using a DFT. Is it possible to study this mechanisms in laptop and DFT programs or other software programs? Thank you, Professor.
So you see, I showed you before one of these slides where we have actually a DFT calculation. Let me see if I can go to that. Here, you see, this is done a DFT calculation. So basically, these are colleagues of us, in this case, are sitting in Sweden, and they calculated this. So they basically take the catalyzer, and then they just put, for example, the oxygen, or here in this case, they put the carbon monoxide, and then they study, let's say, the minimum energy of this one sitting there. So in our case here, we usually do the experiments because we are experts in doing experiments. And of course, there are groups somewhere else in the world. And for example,
I'm not sure if
your voice is breaking, Professor. I cannot hear you.
You know, one of the organizers.
Ala, if you can hear us, we cannot hear him clearly.
Some material.
Ala.
Then she calculates correctly what happens. So nowadays, let's say the most of the catalyzers that we use in our life, they are, let's say, found by empirical things. So let's say there are groups, experimental groups, and then they are probing around. So you take certain material, you add a certain other material, you check that, and so on. So it's, let's say it's a trial and error approach. In the future, it would be the best that theory, let's say, for example, with artificial intelligence or something like that, could predict us some catalyzer that is better suited. Now, for example, here I've shown you we are using rhodium. Let's say that we would make an alloy between rhodium and iridium, let's say. And then you can use, let's say, theoretical approach to study, for example, rhodium, iridium 2, or iridium 2, rhodium, or something like that, to combine such materials theoretically first and see if you can lower certain energies. And if you do this with some artificial intelligence, you, let's say, leave the system free to find some solutions. That would be, in my opinion, the best idea to get to some situation where theory proposes something, and we, as experimentalists, we will later on check if such a material is really behaving better, is really working better in this sense. For us, theory now is just a little bit, it tells us if our experimental things are correct and explains partially things that we observe. But it would be better to do the other way around. That theory predicts us think, and we as an experimentalists, we just check them if they are really good or not. This would, let's say, the resources that we have combine much better with the theory together.
Yeah, exactly. Thank you, doctor. But to do the trial and error over and over may consume a lot of catalyst energy and money in the labs. So the main concept of do modeling and simulation of a catalysis is to make sure that we are avoiding uncertain or undesired product or other stuffs in the reaction. This is just my idea. So I thank you again.
Let me just a second. Let me stop this presentation that I can see you. So again,
sorry, we cannot hear you both. Ala, can you hear us?
And they are using, let's say, programs that are suitable for them. So, for example, if you are doing EFT calculations, so whatever you have, let's say, certain codes, so beam codes, and whatever. And the question is how you can actually address that in a correct way. So, doing calculations is not so easy if you're not an expert. I'm not sure to which point you at your university get enough help from your supervisors, enough, let's say, input to carry out such reactions. So this is a long time process to learn how to actually address such a problem. I'm not sure if I answered your question correctly.
Thank you.
Yes, yes.
I'm muted. No.
I think, can you hear me, Ella, now?
Yes, I can.
I think you have two speakers. We hear some equals. So one of you could,
Unmute. Okay.
yeah, mute himself.
Then I unmute my.
Hey, the other more questions. Sure, how to make the.
I think Adam has a question. Adam.
I to feel something.
I have also some questions in the chat.
I believe it's already. It's already. I mean, this is this guy. And new one. Can somebody else something, tell something so that I can check if I hear you?
Yeah, yes, now we can hear you.
No, then we use my last computer for that case, for this purpose. Just, okay, now I have two computers. I have to unmute. I'll come around.
Yeah.
Okay, so I hope I can hear you. Can somebody tell something?
Yes, can you hear us?
There's still this guy here. Okay, now I can hear you.
Okay. Okay, great. Thanks, Prof. We have a online question. Ala, do you wanna take it or I can say it in the chat?
Come on. I can go to this chat.
You can click. Yes, this is the. Then.
So the question is from Khadija. So she's asking if this technology can be used to treat water and air radioactive pollution. And this is actually what we want to do. So this
Mute yourself.
Okay, now you hear me better? Good. So basically, this is what we are doing. Now you see this pollution, this is what we produce by our cars. So this pollution is when you were in cartoon and a lot of cars are driving around. So all these, let's say, all these pollution that comes out of the cars, of the buses, of trains or whatever you have. And we have to clean this environment. So to clean this environment starts at the beginning to have this directly from the motor, what's coming out of your motor, what's coming out of your engine to clean. So that's why we have this three-way catalyzer that are used very much in the world already. And I mean, another problem are, for example, ships. Ships are producing, there are no cleaning at all. Everything goes to our atmosphere. Now, to reduce, for example, the pollution that is already in air is much more complicated because there you have it in tiny amount. You have to, let's say, clean all the air, and this is much more complicated. So you would need a lot of energy. It's much better to clean, let's say, on the production side. So if you have an industrial plant, you have to clean it there on this industrial plant. So this, let's say, the stuff should not even go to our atmosphere. And in the water, it's similar. So we have to avoid that such, let's say, poisonous stuff goes into the water. Once it is in the water, it's very complicated because you have oceans that are immense. So cleaning an ocean is very difficult. You have to avoid that it gets to the ocean. You have to avoid that some industry puts the products into the water and then the river takes it to the ocean. So it's much easier to do it locally on the production part than later on when this is already in the environment. I hope I answered your questions. So now there are a lot of stuff.
Yes, there is questions from Mohammed.
Okay, the question of Mahmoud is if the modeling is to have a quantitative understanding, quantitative understanding and how such surface structures change. So what I was not talking about today is, of course, if we do such a reaction on a surface, our catalyst can change. So if we have, let's say, a certain facet, and I've told you we have a 1-1-1 facet, we have, let's say, this stepped surface, a 1-1-2. If we do such a reaction, also we change our catalyst, or we can change our catalyst. And such things can actually, in my opinion, very well done with theory. So you put such a material, for example, this CO2, this NO, on a surface, and you can calculate the energies. You put it on some other surface, calculate the energies, and then you can actually see where is this bonding better. So if you have a very strong bonding, this for a catalyst is maybe bad, because then you cannot take it away. Now let's imagine that you have an NO sitting on some corner atom. This sticks very, very tough, and you cannot remove it, but you can calculate it, how strong is such a, let's say, such an adsorption. And if you change now your crystal from, let's say, from a 1-1-1 to this 1-1-2 or the 1-1-3 facet and so on. So how, let's say, these things will change. We can also make the reaction theoretically on the surface. So you combine, let's say, this NO together with another oxygen to make this NO2 or N2O, whatever, and do such things. I believe it's completely able to do such catalytic activity on the surface and to be able to describe this theoretically and then help us as the experimentalist to design such catalysts and try them later on.
Another question from Luay. In what basis catalyzer element has to be chosen? Why is it iron or rhodium or iridium? Is there any mathematical models for that?
There are basic, I mean, this is the point. So there are basic ideas why we choose, for example, rhodium, iridium, and so on. But mainly it comes out from experimental works done in the last century. So if, for example, in the industry, you want to reduce, for example, the CO, then there were people who use different things. They take copper first. Copper does not work. They take iron. Iron works better. They take rhodium. They take iridium. And then this is empirical work first to, let's say, to try around why this happens. So there are some theoretical concepts. It's basically, you see, most of these elements are transition metals. Now, iron, rhodium, iridium, they are transition metals. And it's basically the D bands that are close to the Fermi level. So the D bands, they are filling up by iron, rhodium, iridium, and where they have, let's say, their energy. So their average energy. So if this average energy is in a certain value, for example, 2 electron volts, I do not know now. If they are on 2 electron volts, then this catalyst would be good. For example, platinum is very nice for water splitting. So, and this is because platinum has this average D band at, let's say, 2 electron volts below the Fermi level. And this is very effective then to break this water. Iron has some D band center that is different, and this is very well suited now, for example, for this NO, for this nitrogen combining together with the hydrogen to make this ammonia. So there are some theoretical concepts that you can read about it, in some textbooks, but are not so advanced yet. So there are a lot of things that we have to do still in this sense.
One question from David. Question from Sabri. His question is, when the surfaces of the solid collision, when the surfaces of solids collide with the X-ray diffraction, what are the sub-least activities that can be observed?
I mean, in our case, what we do, I mean, we are not doing X-ray diffraction too much. So we are making X-ray photo emission. So X-ray diffraction is basically from the diffraction experiment, you can learn about the structure on the surface. Now, if you change a surface, let's say we have this 2-to-1 surface and we put a lot of gases, then actually you make a faceting. So you have a part that is 110 and a part that is 111. And this you can study with this X-ray diffraction. So this is, let's say, X-ray diffraction, what it does on your things. What we are studying here is basically X-ray photoemission. So photoemission is we just catch out the electron that the process releases and analyze this electron. So we analyze the energy. From the energy, we learn something, not only which material we have, also the chemical environment of this material. So it's not the same that we have, let's say, a CO sitting, as I've shown you before, on top of a rhodium or in some corner of the rhodium. There's a small shift. And this helps us to understand how catalysts are working. What is sub-least?
The sub.
Ala, I think you missed a question at the top from Ali Yahya. Not sure if you went through it.
Ali Yahya, yes, Ali Yahya. He's saying his question. Thank you for the nice talk. His question is, which techniques is better to understand the issues related to plasma facing materials, fusion energy. In the past, I used modeling methods, for example, molecular dynamic simulation like lamps.
So in my opinion, so this molecular dynamics would help a lot. So DFT gives you some, let's say, some idea what is happening on the surface. But I mean, molecular dynamics will help us because, again, we have different gases on the surface. These gases, they have to move around. So molecular dynamics can address such an issue. It's not the same as you stick an atom and it stays there and it does not move. But for example, this oxygen, it has to move around. It has to go to the place where the CO is sitting to combine with the CO and then go away from the surface. So there are several techniques. All of them are helpful. In my opinion, molecular dynamics is very helpful if it's applied in a correct way. And again, DFT also calculations are also quite nice to really have an idea, for example, how much is a sticking? If this sticking is very strong, you will not be able to remove it. Now, so some of these catalysts, I was not able to show the videos. So for example, in this platinum, these steps atoms are completely stuck with the CO. The CO sits there and nothing can happen. But on this rhodium, for example, on one of these type of steps, this one with the triangle, so this CO is not so sticking so strongly on the step atom and it comes away. So DFT calculations can calculate that. Molecular dynamics later on can calculate how these, let's say, atoms, these atoms can move on the surface, move together, then combine together and leave our surface. So all of them, in my opinion, are quite useful if they are applied in a correct way.
And then, one question from Tijani. He says, can I use a catalyst in the removing of silver and how?
So sulfur, yes. So sulfur is a very important, let's say, contaminant in a certain sense. And sulfur can be quite easy removed, in my opinion, with copper. So copper is very prone to produce copper sulfide. Basically, the copper that we use nowadays is from some minerals that has sulfur, and copper would be quite well to remove sulfur from the surface. There are probably also other materials, but copper would be nice. The point is, it's the question where you have the sulfur. If you have the sulfur in the air, if you have the sulfur in a river or something like so. This is a little bit one has to study, and then if the copper would be a good catalyst to remove that.
Another question from Hanan. She said her question, when introducing curvature into the catalyst surface, is the resulting deformation purely elastic, or could it become plastic, potentially introducing permanent defects such as dislocations or twinning?
Mm-hmm.
And how do you ensure that the crystal structure remains stable under such a curvature?
Okay, I mean, the concept, or maybe I didn't explain it well. So we do not take that crystal and bend it, but we polish that. So it's basically a single crystal, and we're just starting to scrap a little bit things around. So we scrap a little bit here, we scrap a little bit there, and basically it's keeping a single crystal. It's not bent, it's a single crystal. It's exactly the same single crystal as you had before, but now since we shaped that, we polished that in a certain way, we do not do any plastic deformation. So we have still a single crystal, but now we have steps that we are coming out just of the, let's say we cut that, we polished that in a different way. So there's no plastic deformations that we have inside. And also, I mean, defects you have everywhere. You have defects on a single crystal in all places, also in our single crystal. But let's say what we want to address is the steps, and the steps are not coming from defects. This is just out of our polishing. So, for example, you can imagine that you have a rock that has a certain structure, for example, some copper, and then you cut this copper that you have a 111 surface. You cut copper that you have a 100 surface. And now we cut this copper that we have a 111, and now we polish that we have a certain thing. So we are single crystal still, but let's say if we would make a ball out of that, then you have 111 on the top, you have a 100 on the side, another 111 on the bottom, and so on. So such a thing, such a, let's say, circular shape is very difficult to treat. So that's why we are doing, let's say, this cylindrical shape that is easier to address with our methods.
There is another question.
Ala, I think Mujtaba is raising his hand long time ago.
Okay, where is Mujtaba? He can unmute himself.
Thank you very much, Professor Frederik. My question is having 2 points. Point number one, you have not shown us any work of depth profiling by using the ion source and changing the structure under the XBS, and then you checking the making quantitative and qualitative analysis for your samples. Number one. Number two, is there any role for the treatment of this catalyst? Because you have shown us microscopic images, but is there any role for the surface roughness to be changed by changing the experimental conditions? Thank you very much.
So let's start with the first question. The first question was about the depth profile, and we are not doing that. I mean, we just produce our, let's say, what you have there in this photograph that that I have shown you. This let's say this catalyst, this for this Haber-Bosch process, is just how a catalyst in real nature looks like. And then you see there are a lot of these tiny elements, and these tiny elements are actually the let's say nanocrystals, nanoparticles. So these nanoparticles has different shapes. Now, if you have a single crystal, a single atom, you have a single atom. So then you have already 5. Then you're starting to make, let's say, a certain shape. If you have hundreds, then this 100 atoms, they have, let's say, a 111, they have a 110, they have a, for example, a 201 phase, and so on. So nanoparticle is out of that. And what you use in this catalyst, you are using such small things. And these small things, we do not try to modify that. We just, let's say, in order to study such things under certain conditions, we try to artificially create a nanoparticle. So if this nanoparticle have, for example, a 100 phase, then we are using a 100 crystal that is huge, but I mean huge in the sense it's some millimeter, to study that. So we are not going inside, we are not making a depth profile, because the catalytic process usually happens on the surface. So for us, it's not interesting what is below there, because there's a very small or no activity, because the gas interacts at the surface. They interact where where your top atom on the surface is actually situated. So that's why depth profile is not so interesting for us. We do not even study that. And the second question was, just let me remind you, if you can ask again.
Muktaba, if you can repeat your second question.
Yes, the second question was about the role of the surface tension with, in addition to the images that you have seen for your different experimental conditions of the catalyst.
This tension plays a role, of course. I mean, it's not the same as you do such an experiment on a 111 surface. For example, maybe you know, maybe not. So a gold 111 surface is really compact. So it's even more compact than the gold in the bulk. So it is, you compact this by 6% more. So these have really strong surface tension. Once you introduce steps, for example, you release this surface tension. And this surface tension makes that your atoms are a little bit further away, and then catalytic processes, so the sticking of some CO, for example, to such atom is different if the other atoms is a little bit closer or a little bit further away. So tension plays a role, and this is basically one of the reasons why, for example, this 221 or 112 surface are more efficient. One, it's the atom itself that attacks the step, and the other one is coming from the surface tension. So since they're a little bit wider away, the atoms of our catalyst, so this plays a role. And this is also where I was asked before about theory. So theory can address that part. We just studied it, but theory can address it. We can make some model. You see how this actually relaxation takes place, and then we can put again CO molecules or oxygen molecules and study again, let's say, the adsorption energies on top of such structures. And they are different. They are different. And out of this difference, we can learn, for example, if such a material will be a little bit more or a little bit less active. So this is a quite important point that you address.
Okay. Another question from Russia. She's saying, I would like to know, can we use low temperatures synthesis method to produce these nanomaterials, because high temperatures producing of these materials is very difficult.
So I mean, for real catalyst, I do not really know too much how they are produced. So in our case, we are using model catalyst. We are using single crystals that we shape in the way I explained to you. And I can understand that producing such a catalyst with high temperature is difficult, because if you have a high temperature, maybe they melt together, and then you do not have any more the nanomaterial that you want to have. But I do not know too much about the synthesis methods for such things. In our case, since we have single crystals, we buy that single crystals and then we shape it at room temperature by ourselves. We just file them, we cut them, and so on. So everything is done in our case at room temperature. But for really nanomaterials that are used in industrial processes and so on, I do not really know. I mean, the ones that we produce here, for example, we use copper sulfide as a catalyzer and so on. They're produced by completely different methods. Now, they're used by electrochemical methods, or they are produced with some, let's say, shaping and so on. So this question I cannot really answer too much.
Okay, I hope I have read all the questions.
Ala, can I?
Yes.
Thank you, Prof, for the very insightful lecture and talk, and for your patience also with the questions of our participants. It was very wonderful to see this interaction. It's clear that this defined how well we delivered the talk and how well our participants have interest in the topic. I'm just in their behalf, I want to ask you, for all of the participants, we have people from different range in terms of the levels, masters, graduate, senior graduate. And so is there any opportunities? Could you just say a word in terms of the opportunities for them as young researchers looking for any type of opportunities, such as training or even scholarships for master or even PhD within the field or within your lab?
I mean, we are both, so Alain and me. So I mean, I tell you a little bit. So we have certain openings sometimes for postdoc positions in general that you can watch in our internet presence. So Alain can also share the direction out of that. So there's, for example, PhD fair. So we can, that is the reason why Alain is here actually. So she's sitting just here with me. So, so she applied to this PhD fair, and then finally she came here to Spain to carry out her PhD work. So this is happening once a year. And there's another program. So if you're already scientist, there's a program from Spain that is called, how it's called? Women for Science?
Yes, Africa for Science. Women Africa for Science.
So for example, there's an opportunity for women from Africa to apply, for example, for fellowship. So I think it's up to 6 months that they come to Spain. They learn about, for example, in our case, about this, let's say, experimental methods. They can also, again, there are also theoretical groups, so they can interact with theoretical groups. If you can do then later on in Sudan, let's say, some calculations there and so on. So there are opportunities. It would be a little bit the effort to look around. So we in our institute, again, we have this PhD fair that is usually in, I think, in February each year. So this year is just over. And then there again, there's this Women for Africa. This is, let's say, a Spanish-wide program, but I mean, we are taking part of it here in San Sebastián, and there are sometimes openings for postdoc that you just have to look differently on different pages.
Okay.
Thank you so much, Prof. And I hope all the participants have taken the notes of those. Otherwise, we have Ala, so you can always ask her for any clarification.
Okay.
Okay, so thank you very much for listening. And again, you have really great possibilities in the future. So you have the energy, you have the sun, so you can really do a lot of things once this war is over, and making really Africa to one of the leading continents in the world. So we do not have so much sun as you have. You can produce such fuels that are really necessary. You can produce the energy. It's just to learn to get money, let's say, to build it up in the beginning, of course. But I mean, we will not have such resources that you have there, and you really have to be proud that you're part of that you can do such things. So it's very important for you.
Thank you very much.
Thank you. Two last points, Ella, just to have the group picture photo for the session. And as well as there are some people are asking for the PDF and the slides, if is that possible from the prof.
Yes, sure.
Okay,
Good
so
picture.
we will,
Yes.
thank you.
We can.
We will go ahead and try to take the photos. If anyone wants to switch on the camera. Just a moment, so all get
I
ready.
see also some participation. They have some questions. Don't worry, inshallah, we will keep your questions and send it to the professor. He will answer it later.
Who takes the picture? No.
Okay, I think we are
مستعدين
all
نفتح
ready.
الكاميرا بسرعة.
Maybe
Okay.
I put this here, and this is for.
Okay.
Ella, you need to adjust the camera for both of you.
Okay.
Yes, perfect.
Okay, that's good.
Okay, 3, 1, 2. I think I counted wrong, but anyway. Okay, the second page. The third page. Okay, thank you all. I'm done.
Okay.
Ella is yours.
Okay. Thanks again. Thank you very much.
Thank you, Prof. Thanks all.
And you can write the questions to the WhatsApp group, and we will answer them.
Okay, great. Thank you all. Thanks, Ella. Thanks, Prof. Thanks, all participants. And yeah, have a wonderful day.
Thank you.
Ciao.